The world was once teeming with creatures beyond anything we see today, from giants that shook the ground to strange bird-like hunters darting through dense forests. This was Earth over 65 million years ago, during the age of the dinosaurs. They were an entire world of beings that came in countless shapes and sizes, ruling land, sea, and air. They thrived in diverse habitats, surviving countless shifts in climate and landscape, and dominated the planet for over 160 million years. But despite their strength and success, their story came to an end with one of the most dramatic events in Earth's history, one that reshaped life on our planet in ways that are still visible today. Before the giants, the Earth dinosaurs inherited. Long before these famous giants roamed, the world had gone through massive transformations in both climate and life forms, often driven by cataclysmic events and geological shifts. The Earth was already alive with a variety of creatures, both on land and in the oceans. But this life was far different from the plants, animals, and landscapes that would become familiar during the age of dinosaurs. Before dinosaurs, the dominant animals were not reptiles, but rather creatures known as synapsids. Some of these animals, like the sailback Dimetrodon, looked somewhat like reptiles, but were more closely related to mammals. They were the main predators, preying on smaller animals and competing with each other for food and territory. But their dominance did not last forever. The Permian period, which ended around 252 million years ago, brought both a peak in their evolution and a catastrophic end. During this period, Earth's climate shifted dramatically. Vast deserts spread across the supercontinent Pangaea, a massive landmass that was formed when all continents collided and merged together. Conditions were harsh, and life had to adapt to survive in an environment that was both dry and unpredictable. As the Permian period came to a close, an extinction event hit that was even more devastating than the one that would later wipe out the dinosaurs. Known as the Great Dying, this extinction event was the most severe in Earth's history, erasing around 80% of marine species and 70% of land species. This die-off left behind a nearly barren world, with ecosystems struggling to recover. The reasons behind this extinction are complex, with current scientific consensus pointing to volcanic activity, global warming, and ocean acidification as the culprits. Massive volcanic eruptions in what is now Siberia released huge amounts of carbon dioxide, which may have led to deadly climate change and toxic conditions in the oceans. After this extinction, life was almost starting from scratch. The ecosystems that had previously existed were now gone, and it would take millions of years for plants and animals to fill these empty spaces. This mass extinction cleared the way for a new age of life, where new groups would evolve to adapt to the empty landscapes and abandoned roles. During the early Triassic period, around 250 million years ago, life began to make a comeback. Forests regrew, covering the land with a mix of strange plants, including ancient relatives of ferns, horsetails, and cycads. These plants were different from the flowering plants we see today, but they served as the primary vegetation for the time. With these plants came new kinds of animals. As life rebounded, a group of reptiles called archosaurs began to diversify. Archosaurs included many types of animals, such as early ancestors of crocodiles, pterosaurs, flying reptiles, and eventually dinosaurs. They were adaptable and well suited to the changing climate, with their ability to walk upright and breathe efficiently, giving them advantages over other animals in their environment. As the Triassic period progressed, these archosaurs evolved into various forms, slowly spreading across the recovering land. Unlike the Permian's deserts, the Triassic period brought about a more moderate climate, though still with extreme seasonal swings. The Earth's geography was different, with the massive supercontinent Pangaea dominating the landscape, surrounded by a single vast ocean. This arrangement of land and sea meant that much of the inland areas experienced extreme weather, swinging between hot, dry summers and cold, harsh winters. But along the coastlines and in wetter regions, conditions allowed life to thrive, creating diverse habitats and opportunities for new species to evolve. The animals that emerged during this time began to fill new ecological roles. Early amphibians lived around water sources, while other reptiles roamed the land. Some of the larger archosaurs became top predators, while smaller animals adapted to new ways of surviving. Each new adaptation, whether it was better mobility, sharper teeth, or a more efficient metabolism, allowed these creatures to take advantage of the recovering environment. As time passed, some of these archosaurs began evolving into what we would recognize as the earliest dinosaurs, while others became the ancestors of different reptilian groups. But life on Earth did not evolve in a smooth, predictable path. Periodic environmental shifts continued to impact ecosystems. Some of these shifts were gradual, such as the movement of tectonic plates, which slowly changed the shape of continents and shifted climate patterns. Others were more sudden, like volcanic eruptions that released gases into the atmosphere and caused temporary changes in climate. These events constantly shaped life, favoring animals that could survive or adapt to new conditions. The diversity of life continued to grow, with each change pushing animals to evolve or risk extinction. As the Triassic period progressed, another extinction event took place around 201 million years ago. While not as severe as the Permian extinction, it was enough to wipe out many competing species, including several groups of archosaurs and large amphibians. This extinction event was the final push that cleared the way for dinosaurs to become the dominant animals on land. With fewer competitors and plenty of empty niches, dinosaurs quickly diversified into a wide range of forms, from small, quick-moving hunters to large plant-eating giants. By the time the Jurassic period rolled around, dinosaurs had firmly established their presence across much of the Earth. They had evolved unique features that allowed them to thrive in their environment, including lightweight bones, sharp teeth for carnivorous species, and massive bodies for herbivores that would soon grow to extraordinary sizes. Adapting to thrive, how dinosaurs took over ancient ecosystems. Dinosaurs became some of the most adaptable and successful animals on Earth, filling nearly every available habitat and transforming the ancient world they lived in. From the dry deserts to humid forests, dinosaurs managed to carve out a place for themselves, evolving a range of characteristics that helped them thrive in diverse environments. This adaptability was one of their greatest strengths, allowing them to dominate the ecosystems around them for over 160 million years. One of the factors that helped dinosaurs spread across so many regions was their ability to walk with legs positioned directly under their bodies. Unlike other reptiles, whose legs often spread out to the side, dinosaurs had an upright stance that made movement more efficient. This design allowed them to travel over long distances, move quickly when necessary, and conserve energy. In many habitats, this upright posture gave dinosaurs a distinct advantage over other large animals, like ancient reptiles, that were more restricted to specific environments and less able to cover as much ground. Some dinosaurs became specialized for hunting, with sharp teeth, powerful jaws, and strong limbs for capturing prey. These carnivorous dinosaurs, such as the early theropods, became skilled predators, taking on the role of top hunters in their ecosystems. They had a lightweight build that allowed them to move quickly, and their sharp claws and teeth made them efficient killers. This role as a top predator helped them control the populations of other animals, creating a balanced ecosystem where prey species couldn't dominate and overconsume the available plant life. Herbivorous dinosaurs like the early sauropodomorphs, which later evolved into the giant long-necked sauropods, developed specialized teeth and jaws for grinding tough plant material. These dinosaurs often traveled in herds, which offered protection from predators and allowed them to graze across large areas. In some cases, these plant eaters grew to massive sizes, becoming nearly untouchable to smaller predators due to their bulk alone. As large herbivores, they shaped their habitats, often clearing forests and spreading seeds as they moved from place to place. Some dinosaurs adapted to life in dry deserts, where food and water were often limited. Creatures like the ceratosaurs and some smaller theropods evolved to become efficient hunters, able to conserve water and survive long periods between meals. In wetter areas, dinosaurs adapted to life in dense forests and along riverbanks. Forested environments offered a variety of plants for herbivores and numerous hiding spots for both prey and predators. Long-necked herbivores could reach tall trees for food, while smaller, agile dinosaurs could weave through undergrowth. This allowed them to find food sources that other large reptiles couldn't reach, giving them an edge in the competition for resources. Earth's climate and landscape were far from stable, with periods of cooling, warming, and even volcanic activity altering the environment. Dinosaurs evolved traits that allowed them to endure these changes, and even benefit from them. When conditions became cooler, certain dinosaurs developed feathers, which not only helped with warmth, but may have also given them an edge in other ways, like attracting mates or camouflage. Feathers would later be essential to the evolution of birds, which arose from a group of small theropods, showing how dinosaurs continued to adapt in new and surprising ways. As the Jurassic period gave way to the Cretaceous, dinosaurs continued to evolve and spread across the planet. They adapted to new climates and habitats as the continents slowly began to drift apart, creating new landforms and separating populations. These changes led to even greater diversity among dinosaurs, with new species evolving to fill the roles left by others, or to exploit new opportunities. This constant adaptation and evolution allowed dinosaurs to maintain their dominance over other animals, including mammals, which were mostly small and nocturnal at the time. Signs of stress, environmental shifts, leading to the Cretaceous crisis. As the age of the dinosaurs moved toward its end in the Cretaceous period, Earth was undergoing changes that would prove challenging to many forms of life. While dinosaurs had endured and adapted to environmental shifts before, this time the changes would be on a scale that threatened entire ecosystems. The planet was entering a period marked by climate fluctuations, volcanic eruptions, and shifting sea levels, all of which began to unsettle the once stable environments dinosaurs called home. The Mesozoic era, which had provided a warm and relatively stable climate for much of the dinosaurs' reign, was beginning to experience greater temperature swings, while earlier periods had their warm spells, which were favorable for reptiles and other cold-blooded animals. The late Cretaceous was marked by fluctuations that introduced more variability. These climate shifts impacted the vegetation that dinosaurs relied on, especially the large herbivores that needed abundant plant life to sustain themselves. When temperatures dropped, plant growth slowed, and certain species found it harder to access the food they needed to survive. In turn, this affected the carnivorous dinosaurs that preyed on these herbivores, creating a domino effect through the food chain. The volcanic activity during this period was another major stressor on the planet's ecosystems. Intense volcanic eruptions, particularly in the region now known as the Deccan Traps in India, released massive amounts of lava and gases into the atmosphere. These eruptions weren't just isolated events. They were part of a sustained period of volcanic activity that lasted for hundreds of thousands of years. The volcanic gases created acid rain, which harmed plants and animals. The ash and particles released into the atmosphere blocked sunlight, leading to cooler temperatures and reduced sunlight for photosynthesis. Plant life suffered, weakening the base of the food chain that so many animals, including dinosaurs, depended on. Initially, the volcanic particles created a cooling effect by blocking sunlight. But as the particles settled, the long-lasting presence of carbon dioxide trapped heat, leading to warming. These extreme swings between cooler and warmer climates created instability that affected life forms adapted to specific temperature ranges. For dinosaurs and other animals that were highly specialized, these changing conditions made it harder to thrive in the habitats they had long dominated. As tectonic plates moved, ocean basins shifted, causing the seas to advance and retreat over large areas of land. During the Cretaceous, sea levels were high, flooding vast parts of the continents and creating shallow inland seas. These shallow seas changed the composition of the land, impacting the types of plants and animals that could survive there. Where forests and plains had once supported herds of herbivores, rising waters turned these regions into marshy or semi-aquatic environments. For some dinosaurs, these changes in habitat meant they could no longer find the food or shelter they needed. Coastal areas that had once been rich with plant life became inhospitable, reducing the living space available to terrestrial animals. These rising seas also impacted marine life, disrupting ecosystems that were crucial to the food supply for both sea creatures and coastal land animals. Marine reptiles, fish, and smaller organisms that depended on stable coastal environments were forced to adapt or relocate, which put stress on the overall food web. For larger marine reptiles like mosasaurs, these shifts in sea levels and the availability of prey created additional survival challenges. Some species could adapt to new environments or migrate, but others found it more difficult to adjust, leading to declines in their populations. These changes in marine ecosystems indirectly affected dinosaurs and other land animals by disrupting the balance of the larger biosphere they depended on. Flowering plants, or angiosperms, were rapidly evolving and spreading during the late Cretaceous, gradually transforming the landscape. These new plants brought about a shift in plant communities, with more diverse flowering plants taking the place of earlier ferns, cycads, and conifers that many herbivorous dinosaurs had traditionally relied on. For some herbivores, this meant they had to adapt to new types of food, which could be difficult if their bodies weren't suited to digesting the tougher, more fibrous vegetation of flowering plants. Dinosaurs that couldn't adapt to these dietary changes faced added pressure to survive in a world that was becoming less familiar. Mammals, although still small compared to dinosaurs, began to spread and diversify, which created additional competition for food and resources, particularly for smaller dinosaur species that fed on similar plants or small prey. This competition may not have directly threatened larger dinosaurs, but it added yet another layer of pressure in an already stressed ecosystem. These gradual but relentless shifts in the environment and ecosystem began to destabilize the delicate balance that had allowed dinosaurs to flourish for millions of years. While they had survived previous changes, the combination of volcanic activity, climate fluctuations, sea level changes, and new competitors created a cumulative impact that began to strain their populations. As time went on, these factors intensified, placing dinosaurs in an increasingly precarious position as they struggled to adapt to a world that was rapidly transforming. The environmental changes leading up to the end of the Cretaceous set the stage for a major crisis, leaving ecosystems fragile and vulnerable. Though they were resilient creatures, capable of adapting to many challenges, the growing number of threats made it difficult for dinosaurs to keep up. With each new shift in climate, each eruption, and each rise or fall in sea levels, the ecosystems that supported dinosaur life grew more unstable, setting the stage for an event that would change Earth's history forever. The Chicxulub impact, a day like no other in Earth's history. About 66 million years ago, Earth experienced an event so powerful and sudden that it changed life on the planet almost instantly. The Chicxulub impact, a massive asteroid collision near what is now Mexico's Yucatan Peninsula, marked one of the most cataclysmic days in Earth's history. This single impact unleashed forces equivalent to billions of nuclear bombs and sent waves of devastation rippling across the planet. The asteroid, estimated to be over 6 miles wide, had been traveling toward Earth for millions of years. Moving through space at speeds of up to 45,000 miles per hour, it struck Earth with a force of nearly unimaginable magnitude. The impact zone, located near the present-day town of Chicxulub, was obliterated in seconds as the asteroid made contact. Within moments, the kinetic energy from its movement was converted into an intense release of heat and force. Rock and debris were vaporized at the impact site, launching molten fragments high into the atmosphere. The energy released by this collision was greater than any natural disaster Earth had ever seen, surpassing even the most powerful volcanic eruptions and earthquakes by orders of magnitude. The initial explosion created a massive crater around 120 miles wide and more than half a mile deep, displacing an enormous volume of rock, soil, and water. This area of the planet was flattened in an instant as shockwaves radiated outward from the impact zone. These shockwaves traveled through Earth's crust, triggering earthquakes that were felt thousands of miles away. In nearby areas, the ground trembled, cracked, and split open. Entire landscapes were restructured as hills and valleys were flattened or uplifted by the intense seismic activity. As fragments from the blast scattered across the atmosphere and the impact winter began to take hold, fires raged across entire continents, while oceans were disrupted by tsunamis and chemical changes. The asteroid impact left a deep scar on the planet, transforming it from a lush, thriving world into a dark, smoke-filled wasteland. The intense energy of the impact triggered waves of fires, extreme temperatures, and chemical storms, all of which would have immediate and lethal effects on life both on land and in the seas. The friction and pressure of the asteroid's rapid entry into Earth's atmosphere caused it to burn with white-hot intensity, heating the surrounding air to extreme temperatures. The immense heat from the impact created fireballs that ignited forests and grasslands within hundreds of miles. Anything within close range, including plants, animals, and even solid rock, was scorched and vaporized. Across continents, these fires consumed entire ecosystems and habitats into smoldering fields of ash. Huge columns of smoke and ash filled the air, carrying charred particles high above the land and blocking out the sun. From a distance, the sight would have been one of rolling waves of smoke, darkening skies, and a horizon glowing red as flames tore through habitats. Animals caught in the flames had little chance of survival. Dinosaurs, mammals, birds, and insects were all equally affected. While some creatures managed to escape, fleeing into burrows or escaping toward the few remaining safe zones, many were simply trapped. The fires spread faster than animals could move, especially the large plant-eating dinosaurs. As these fires consumed vast areas of land, they left behind a charred, lifeless terrain. Whole ecosystems vanished as the flames left little room for plants, trees, or wildlife to recover quickly. The impact triggered a phenomenon known as an impact winter. Dust, ash, and tiny particles were blasted into the atmosphere and carried high above the planet's surface. As these particles spread across the globe, they formed a dense cloud that plunged the Earth into darkness. Days turned into a cold, eerie twilight, where sunlight struggled to penetrate the thick layer of soot and ash. Photosynthesis slowed or stopped in many places. Without sunlight, plants couldn't produce food, and animals that relied on plants soon found themselves without a steady food source. This effect was particularly devastating for large herbivorous dinosaurs and the predators that hunted them. The cooling effect of this dust cloud rapidly altered Earth's climate. Within days, temperatures began to drop, particularly on land where the sun's warmth was most needed. Areas that had once been warm and humid turned cold and inhospitable. Even in tropical regions, temperatures fell sharply, creating an unfamiliar and hostile environment for creatures accustomed to stable climates. Rain patterns shifted, leading to unusual droughts in some areas and heavy flooding in others. The climate shock caused many species to perish in a short span of time, as they could not adjust to the rapid changes in their surroundings. The debris launched into the atmosphere eventually fell back to Earth, creating what scientists call a global firestorm. As fragments of rock and dust rained down, they re-entered the atmosphere, heating up as they descended. This created a series of smaller fireballs that blanketed the sky, igniting surface fires across huge regions and spreading smoke and ash. These fires released large amounts of carbon dioxide and other gases into the atmosphere, amplifying the greenhouse effect. Even as the skies darkened, a secondary warming began, caused by the layers of greenhouse gases trapping what little heat remained. The asteroid created massive tsunamis that radiated outward across the seas. Waves hundreds of feet high crashed onto shores, sweeping away coastal ecosystems and wiping out countless marine species. Coral reefs, shallow water habitats, and coastal mangroves were all impacted by the force of these waves. Marine animals that couldn't escape to deeper waters were caught in the destructive wake. The impact stirred up sediments from the ocean floor, releasing sulfur compounds and other chemicals into the water. These chemicals, combined with the cooling and lack of sunlight, altered the ocean's chemistry, causing oxygen levels to drop. Marine species that depended on stable oxygen levels faced a sudden and lethal challenge. As if the fires, cold, and food shortages were not enough, another deadly threat emerged: toxic rain. When the asteroid hit, it vaporized vast quantities of rock, including large deposits of sulfur and other elements. These elements combined with water vapor in the atmosphere to form highly acidic compounds, creating what scientists call acid rain. This rain fell across continents and oceans, burning through plant leaves and contaminating the soil. Many plants that had survived the initial fires now had to withstand acid rain that stripped their leaves and damaged their roots. The acid rain also seeped into rivers, lakes, and seas, affecting fresh water and marine life. Fish, amphibians, and other water-dwelling animals found themselves in environments that were suddenly corrosive and toxic. In the ocean, corals and shelled creatures like mollusks were particularly vulnerable, as the acidified waters weakened their calcium-based structures. Coral reefs, the underwater havens of biodiversity, began to disintegrate under these harsh conditions. Species that depended on these structures for shelter or food were left without homes, contributing to further ecosystem collapse. Ecosystems across the globe lay in ruin, and many food chains had been completely disrupted. Species that had once flourished suddenly found themselves in a world without the resources they depended on. Large plant eaters, such as the enormous sauropods, struggled to find enough food to sustain their massive bodies, while carnivores faced a scarcity of prey. As the global firestorm died down and the dust clouds gradually dispersed, Earth's climate remained altered. Temperatures began to recover, but ecosystems had been irrevocably changed. Forests, once dense with plant life, had been replaced by burned-out landscapes. Many species had gone extinct, leaving gaps in the ecosystem that would take millions of years to refill. The delicate balance that had supported life for so long was now skewed, with large species struggling the most to survive in the altered world. For smaller creatures, particularly mammals, the conditions proved more manageable. These animals could find shelter, scavenge for food, and reproduce more quickly than larger species. They didn't require as much food to survive, and their ability to adapt and find refuge in small spaces allowed them to endure the changing environment more effectively. In a way, the impact set the stage for a new era, one in which smaller, adaptable animals would have the chance to thrive. A different apocalypse, the role of volcanism in the Deccan traps. While the Chicxulub impact sent Earth into chaos, another powerful force had already been reshaping the planet. Thousands of miles away, a vast volcanic region known as the Deccan traps had been erupting hundreds of thousands of years. This area, now in present-day India, was a series of massive lava flows that covered the landscape in layers of solid rock created by intense volcanic activity. These eruptions were not like a single explosion from a volcano. Instead, they were continuous and stretched out over a 600,000 to 800,000 year time period, forming one of the largest volcanic provinces on Earth. The Deccan Traps eruptions released unimaginable quantities of lava, covering areas as large as modern European countries in molten rock. As these eruptions continued, they released gases and particles into the atmosphere, affecting the global climate in ways that were both immediate and long-lasting. Each time lava erupted, it sent plumes of ash and gas high into the sky, carrying dangerous compounds that could travel vast distances across continents. The release of gases, particularly carbon dioxide and sulfur dioxide, added to an already unstable environment. One of the main consequences of these continuous eruptions was a gradual but steady warming effect on Earth's climate. The release of carbon dioxide, a greenhouse gas, created conditions similar to those seen today with modern climate change, but on an even larger scale. Over time, the atmosphere began to trap more heat, causing temperatures to rise around the world. For plants and animals adapted to stable, cooler climates, this slow but steady heating disrupted their habitats and put stress on entire ecosystems. Forests in particular struggled as the changing climate affected growth patterns, leading to shifts in vegetation that rippled through the food web. Sulfur dioxide had a different but equally destructive effect. When sulfur dioxide mixed with water vapor in the atmosphere, it created acidic compounds that would fall as acid rain. Unlike the acid rain that came from the Chicxulub impact, this acid rain persisted for far longer, affecting both land and sea. Forests exposed to the rain began to show signs of stress, as the acidic water burned through leaves and affected plant growth. Over time, these effects altered entire plant communities, slowly reshaping forests and plains, which in turn affected the animals that relied on these plants for food and shelter. Acid rain from the Deccan traps flowed through rivers and streams, eventually reaching the seas, creating pockets of more acidic water that harmed delicate marine ecosystems. Coral reefs, already affected by changes in sea temperatures, faced even greater challenges. The acid weakened the calcium structures that corals relied on to build their reefs, causing sections of these underwater habitats to dissolve. Shelled animals like mollusks, essential parts of the marine food chain, found it harder to maintain their shells, leading to a gradual decline in their populations. Fish and other marine creatures dependent on coral reefs and shelled animals for food and shelter faced a scarcity of resources, leading to a decline in species diversity. The sheer volume of the gases released also created shifts in weather patterns. Some regions experienced prolonged periods of drought, while others faced heavy rainfall. These shifts disrupted ecosystems on land, affecting plants and animals that had become accustomed to stable seasonal patterns. In areas hit by drought, plants struggled to survive, impacting herbivores and the carnivores that preyed on them. In regions with excess rainfall, flooding became a problem, creating conditions where many species found it difficult to thrive. The changes brought by the Deccan Traps eruptions were slow but persistent, acting like a background force that steadily reshaped Earth's biosphere. Eruptions also brought up heavy metals like mercury and lead from deep within the Earth. These metals found their way into water supplies, soils, and eventually into the food chain. Plants absorbed these metals from the soil, and as herbivores fed on these plants, the metals accumulated in their bodies. Predators consumed these herbivores, leading to an even higher concentration of toxins as they moved up the food chain. Over time, the presence of these toxic metals began to affect the health of larger animals, including some dinosaur species. Some researchers suggest that the buildup of these metals may have weakened immune systems or caused other health problems in dinosaur populations, contributing to their eventual decline. As lava covered vast areas of land, it buried plant life and reduced the amount of photosynthesis taking place. This decrease in plant activity led to a reduction in the oxygen output, which, though slight, may have been enough to affect animals that relied on high oxygen levels. In the oceans, the warming effect from carbon dioxide release created layers of warm water that trapped cooler water below. This layering prevented oxygen from circulating properly, leading to areas of low oxygen or dead zones, where marine life found it difficult to survive. By the time the Chicxulub asteroid struck, ecosystems were already stressed. Plants and animals had been facing a slow but steady environmental shift. The combination of volcanic and impact-related effects proved devastating, as species weakened by nearly 1 million years of volcanic activity now faced an abrupt and catastrophic event that changed the planet overnight. This dual assault from volcanic and impact events created a cascade of environmental changes that ultimately shaped the future of life on Earth, clearing the way for the rise of new species in the aftermath. The shadow of extinction. Gradual declines before the impact. Long before the asteroid struck, some species of dinosaurs and other ancient animals were already seeing their populations shrink. Scientists studying the fossil record found that while many species continued to thrive, others seemed to face challenges that were not directly tied to the final catastrophic event. This slow and steady decline tells a story of a world in flux, with ecosystems subtly changing in ways that made life harder for many species. One of the dinosaur groups showing signs of a gradual drop in numbers were the hadrosaurs, or duck-billed dinosaurs. Fossil records from North America suggest that toward the end of the Cretaceous, these large herbivores were less common in some regions than they had been earlier in the period. For much of the late Cretaceous, hadrosaurs had been among the most successful plant-eating dinosaurs, their flat beaks adapted for crushing and grinding plant material. These dinosaurs were well suited to grazing on ferns, flowering plants, and other vegetation in their ecosystems. Yet, as climates shifted and habitats changed, the plants they relied on also began to change, possibly causing stress to the species adapted to specific diets. This drop in the abundance of certain plants may have left hadrosaurs struggling to adapt to new vegetation patterns, leading to lower survival rates and fewer young reaching adulthood. Triceratops and other ceratopsians also faced challenges. Like hadrosaurs, these horned dinosaurs were major herbivores and lived in herds, feeding on a variety of plants. However, evidence suggests that some ceratopsian populations were starting to decline as well, with fewer individuals represented in late Cretaceous fossil layers. Changes in vegetation and increased competition with other herbivores may have been part of the reason for their decline. Other plant eaters, like the ankylosaurs and certain sauropods, continued to fill ecological niches, and competition for food may have intensified as environmental conditions changed. These small but consistent changes added to the stress on Triceratops populations and may have reduced their numbers over time. Predators like the infamous T-Rex depended heavily on large herbivores for food. If herbivore populations were already declining, it could have had a direct impact on predator populations as well. Fossil evidence hints that young tyrannosaurs, which likely faced high mortality rates, even in stable environments, may have struggled to find adequate prey if food sources became less predictable. As these predatory dinosaurs relied on a thriving ecosystem with plenty of plant eaters, any decrease in herbivore populations would have rippled up through the food web, affecting predators at the top. Marine reptiles such as mosasaurs and plesiosaurs were some of the largest ocean predators, occupying a role similar to that of whales today. These creatures relied on abundant fish and smaller marine reptiles, which in turn depended on healthy populations of plankton and other microorganisms in the oceans. But fossilized remains indicate that the diversity of marine reptiles had been gradually shrinking in the late Cretaceous. Several factors may have contributed to this, including shifts in sea levels and changes in ocean temperatures. During the late Cretaceous, shifting tectonic plates caused sea levels to rise and fall over time, altering coastlines and the shape of shallow seas. In some areas, rising sea levels flooded land areas, creating new, shallow marine environments. But in other places, sea levels dropped, exposing former seabeds and leaving marine species without their usual habitats. These changes forced many coastal and shallow water creatures to adapt quickly or move to new areas to survive. Coral reefs, which supported a variety of marine life, also faced stress from these fluctuations. Fossil evidence shows that reefs declined in some areas, potentially affecting food supplies and shelter for numerous marine organisms. Flowering plants, or angiosperms, had become more common in the Cretaceous and were gradually replacing the older ferns, cycads, and conifers. While some herbivorous dinosaurs adapted to this shift, others were more specialized and may have struggled with these changes. Large sauropods, which had dominated earlier periods, had already begun to decrease in diversity, and some researchers believe this may have been linked to shifts in vegetation types. These changes may not have caused an immediate crisis, but would have gradually impacted species adapted to older types of plant life. Volcanic activity from the Deccan Traps released vast amounts of carbon dioxide, warming the climate over long periods, while sulfur dioxide caused periodic cooling episodes, creating short-term climate swings. This unstable climate, shifting between warmer and cooler periods, may have disrupted seasonal patterns that plants and animals relied on. For example, plants that depended on regular seasonal changes for reproduction could have found it harder to thrive, and the animals that fed on these plants would have felt the effects. Animals used to predictable wet and dry seasons might have struggled with irregular rainfalls or temperature shifts, which could affect food availability and breeding patterns. Fewer fossilized nests have been found in some areas, suggesting lower reproductive success in certain dinosaur groups. If fewer young dinosaurs were reaching adulthood, it would eventually lead to a drop in adult populations over time. Chronicles in stone, how the fossil record tells of the end times. The fossil record holds a unique, layered story of life's endurance and eventual end in the days of the dinosaurs. Rocks and fossils buried deep within Earth's crust tell scientists about the end of the age of the dinosaurs. Layers of sedimentary rock, each representing an era or event, reveal how dinosaurs thrived, struggled, and eventually vanished. By carefully studying these layers, paleontologists can reconstruct the sequence of events, almost like reading pages from an ancient book, revealing how life changed before and after the cataclysmic asteroid impact. One of the most powerful tools for scientists is the thin, dark layer of clay found in sediment deposits worldwide. This layer, known as the KPG boundary, marks the line between the Cretaceous K and Paleogene PG periods. It is a clear dividing point in Earth's geological history, the moment when dinosaurs disappeared and mammals began to rise. The KPG boundary holds a rare and distinct mix of elements, including iridium, a metal uncommon on Earth's surface but found in higher amounts in meteorites. This iridium layer is one of the key clues that pointed scientists toward the impact theory, suggesting that a massive object from space collided with Earth around 66 million years ago. The high concentration of iridium acts like a fingerprint, linking this layer of rock to a cosmic event. Embedded in this layer are tiny glass beads called tektites, formed from molten rock thrown into the atmosphere by the impact. These tektites fell back to Earth, scattering across the planet and embedding themselves in the sediment as a silent testament to the explosive energy of that day. But the KPG boundary is more than just a line of iridium. It also contains traces of ash and soot, remnants of massive wildfires that burned forests and ecosystems after the impact. This soot is like the ghost of ancient forests that were set aflame by the intense heat and shockwaves from the asteroid. Fossilized charcoal fragments found in this boundary layer support the idea of these vast fires, indicating that, in the wake of the impact, much of Earth's vegetation went up in flames. These fires would have devastated habitats, leaving animals without shelter and food, and disrupting ecosystems on a massive scale. In some places, fossilized remains of dinosaur bones and teeth are found just below the KPG boundary, marking the final days of these creatures. The positioning of these fossils shows that dinosaurs were still present up until the impact event, hinting that their extinction was sudden and widespread. These fossils, often found near the KPG boundary in North America and Asia, reveal a diverse array of species that once thrived in the Cretaceous period's last days. The arrangement of these fossils suggests that dinosaurs were still well represented in their ecosystems, with different species filling roles as predators, grazers, and scavengers. This fossil evidence paints a picture of a thriving dinosaur community that vanished almost overnight. In the sediments from the end of the Cretaceous, scientists have found abundant evidence of fern spores. Ferns are hardy plants that can rapidly recolonize land after a fire or disaster, often referred to as disaster species. The sudden increase in fern spores, known as a fern spike, is found in sediments just above the KPG boundary. This spike in fern spores provides evidence that ferns were among the first plants to grow back after the asteroid impact and the widespread fires that followed. These ferns likely grew in soil left exposed after the destruction of forests, showing how life attempted to recover amid the devastation. Paleontologists also study microfossils, tiny remains of organisms like pollen, spores, and plankton, to understand how life responded to the environmental upheaval. In marine sediment layers near the KPG boundary, scientists have discovered a sudden drop in the diversity of plankton species. Before the impact, the oceans teemed with various microscopic organisms, each playing a role in the food web. But after the asteroid hit, many of these plankton species disappeared. This loss would have disrupted the entire marine ecosystem, impacting fish and other animals that depended on plankton for food. Bone beds, or mass graves of fossilized bones, offer a glimpse into how animals, possibly in their last moments, gathered in dwindling numbers. Some of these bone beds contain mixed remains of different dinosaur species, suggesting they may have gathered around shrinking water sources as environmental conditions deteriorated. These sites offer paleontologists a unique view into the social behavior of dinosaurs during times of stress, possibly herding together for protection or to access the few remaining resources. In these beds, paleontologists find evidence of herbivores and carnivores alike, all showing signs of distress, malnutrition, or injury. The fossil record also reveals patterns of survival among certain species. Some small mammals, birds, and reptiles managed to endure the extinction event, showing how certain adaptations may have helped them survive where larger animals did not. Fossilized remains of early mammals indicate that these creatures lived in burrows or sheltered areas, which may have protected them from the worst effects of the impact and its aftermath. Small size, ability to find shelter, and diets that could include a range of food sources likely gave these creatures an edge in such harsh conditions. Their fossils show that life, although reduced, continued, adapting to the stark new realities of a post-impact world. In the fossil layers above the KPG boundary, the absence of large dinosaur bones tells a silent story. After the boundary layer, no more remains of massive herbivores or terrifying predators appear, signaling a clear and undeniable end to an era. The rocks no longer contain Triceratops bones or the tooth marks of T-Rex. Instead, the remains of smaller animals and different plant species start to fill the layers, as new ecosystems slowly develop in the absence of the giants. This absence is one of the most haunting signs in the fossil record, highlighting the magnitude of the extinction and the loss of creatures that had once ruled the Earth. Lost in the ashes, dinosaurs that perished in the first waves of extinction. The first dinosaurs to suffer were likely those that thrived in warm, stable climates with predictable food sources. Many of these were large, plant-eating dinosaurs that relied on vast quantities of vegetation to survive. These herbivores, like the hadrosaurs and certain types of ceratopsians, often needed to consume massive amounts of food daily to sustain their bulk. When fires scorched the land and burned through forests, their primary food sources were destroyed almost immediately. Without enough plant life to graze on, these dinosaurs quickly faced starvation, unable to adapt in time to the sudden, scorched landscapes around them. The larger size that had once helped them thrive now worked against them in an environment stripped of resources. The impact's shockwave and heat also likely caused the immediate extinction of many small and medium-sized dinosaurs that lived near coastal areas. Dinosaurs like certain raptors and smaller herbivores had adapted to environments where water was plentiful and temperatures were moderate. However, the immense waves, created by the force of the asteroid's collision with the ocean, devastated coastlines and flooded low-lying areas. These tsunamis not only swept away plants and animals, but also drastically altered the landscape itself. Creatures that had once depended on these areas for water, food, and shelter now found their habitats either destroyed or entirely underwater. With nowhere to retreat and limited resources, these dinosaurs would have had little chance to survive in the chaotic aftermath. Predators that specialized in hunting particular types of prey were especially at risk. For instance, certain theropod dinosaurs, large carnivores that primarily hunted herbivores, quickly faced a crisis. The competition for whatever remained alive intensified, but in the harsh, resource-scarce environment, even the top predators couldn't escape the impact. As their prey disappeared, so did these specialized hunters, who could not adapt fast enough to the sudden lack of food. The initial wave of extinction also claimed many dinosaurs that depended on complex ecosystems like wetlands, rivers, and forests. Certain species of ankylosaurs and stegosaurs, armored herbivores that were adapted to foraging in dense vegetation, found themselves in desperate situations as wildfires raged across the landscape. Forests, which had provided these dinosaurs with food and cover, were reduced to ashes in a matter of hours or days. Without their natural habitats and food sources, these creatures faced immediate hardships. Some dinosaurs relied on specific environmental cycles and stability to survive, and the sudden breakdown of these cycles proved deadly. Hadrosaurs, for example, are thought to have migrated seasonally to find food in favorable climates. These migratory patterns were closely tied to weather cycles that had existed for millions of years. However, after the impact, these cycles were thrown into chaos. With the atmosphere darkened by dust and debris, seasonal cues likely became confused or disappeared entirely. The sudden changes would have disrupted breeding cycles and migration, leading to rapid declines in population as these species could not cope with the loss of the familiar patterns that had guided them for generations. The dinosaurs' delicate eggs and young offspring faced nearly impossible odds in the new environment. Many dinosaurs laid eggs that required stable temperatures and specific conditions to hatch. The intense fires, cold snaps, and toxic rains that followed the impact created conditions unsuitable for egg incubation. Dinosaurs that might have survived as adults couldn't replenish their populations as fewer and fewer eggs hatched. Baby dinosaurs, which needed protection and a steady supply of food, faced an environment where resources were scarce and threats were everywhere. Coastal marine reptiles like mosasaurs and plesiosaurs likely experienced the impact's effects first. Waves from the impact zone rippled outward, reaching distant shores and wreaking havoc. Many marine species were washed ashore or trapped in unfamiliar environments where they couldn't survive. Those that lived further out at sea faced declining prey populations as phytoplankton began to die off from lack of sunlight. Under the microscope, how fast did the extinction unfold? The extinction of the dinosaurs is often described as a sudden event, but piecing together how quickly it happened is still a complex challenge. While the Chicxulub impact unleashed a cascade of destruction, scientists continue to investigate whether the extinction wiped out dinosaurs almost instantly, or whether some managed to survive for a short while in isolated pockets. With only the fossil record to guide them, researchers have looked closely at sediment layers, chemical traces, and fossils themselves to better understand how rapidly life was wiped from the Earth. One major area of focus is the KPG boundary. By analyzing the thickness and distribution of this iridium layer across multiple sites, scientists can estimate how quickly this layer formed. In many locations, the boundary is only a few millimeters thick, suggesting that the deposit was rapid and widespread, likely settling within days to years after the impact. However, the aftermath of the impact may have stretched on for much longer, creating conditions that were lethal to many forms of life. Researchers have found that different dinosaur species appear to have died out at slightly different times. This pattern suggests that while some dinosaurs might have perished almost immediately, others could have lingered in small populations for a short period. Some scientists theorize that smaller or more adaptable dinosaurs, especially those living far from the initial impact site, could have survived briefly before facing the harsh conditions brought on by a nuclear winter scenario. This temporary survival would not have been easy, as these dinosaurs still faced a world filled with ash, cold temperatures, and limited food sources. However, their potential to last a few years, rather than days or months, has led researchers to consider a more gradual extinction timeline for some groups. One approach to understanding the extinction's pace involves studying fossilized pollen and plant remains found alongside dinosaur fossils. These ancient plant materials offer clues about the environmental conditions before, during, and after the impact. Before the asteroid struck, the fossil record shows evidence of lush, diverse plant life. But in layers directly above the impact boundary, pollen records shift dramatically, indicating that many plant species disappeared or were replaced by ferns and other hardy plants. The sudden spike in fern spores directly above the impact layer hints that forests may have died off rapidly, likely within days to weeks of the asteroid collision, leaving landscapes bare and forcing herbivorous dinosaurs to starve soon after. Some fossil beds, found far from the impact zone, show unusual patterns in their layering, with fish fossils stacked in ways that suggest they died in waves. These patterns have led to theories that toxic rains and shock waves from the impact spread gradually, creating a ripple effect across different habitats. In these fossil layers, large groups of fish appear to have died off in close succession, possibly from poisoned water sources. Fossil evidence shows that while many dinosaurs disappeared, some small mammals and bird-like dinosaurs managed to survive. These animals, likely better suited to hide or find alternative food sources, provide a contrasting story to that of the larger dinosaurs. Mammals, with their small size, burrowing behaviors, and varied diets, may have been better equipped to find food and shelter in the chaotic world following the impact. Their survival supports the idea that the extinction may not have been instantaneous, as some small pockets of life were able to hold on in the aftermath, gradually adapting to the new, harsher conditions. So, while the largest dinosaurs faced a sudden and devastating decline, other life forms experienced a slower struggle for survival. Another clue lies in the fossilized shells of marine organisms, which record changes in ocean temperature and chemistry. By examining these shells, scientists have found that ocean temperatures dropped quickly after the impact, a change that could have taken only a few years. This sudden cooling would have affected marine dinosaurs and other large reptiles, as well as many types of fish and invertebrates that were not adapted to such rapid environmental shifts. Over time, as the cooling persisted, these creatures faced increasingly challenging conditions, with many species unable to adapt quickly enough to the colder, darker oceans. Rock layers from the KPG boundary show patterns of heavy erosion, suggesting intense storms, floods, and other natural disasters in the years after the impact. These disturbances would have added to the stresses faced by surviving dinosaurs, eroding the land, washing away vegetation, and disrupting rivers and lakes. Areas that might have offered some refuge were quickly transformed into barren landscapes, further narrowing the chances for any lingering dinosaur populations to survive. The presence of volcanic activity in the Deccan Traps complicates the timeline even further. Volcanic eruptions would have started before the asteroid impact and continued for hundreds of thousands of years afterward, filling the atmosphere with ash and gases. If these eruptions were occurring alongside the immediate effects of the asteroid, the extinction may have played out in a staggered fashion. Some dinosaurs may have died from initial impact effects, while others faced long-term declines from the ongoing volcanic disruptions. The layering of volcanic rock and ash found alongside the impact layer offers clues that this combined impact volcanism scenario could have made the extinction an even more drawn-out event for certain species. The greenhouse effect, extreme temperatures and ecosystem collapse. Following the darkness and freezing temperatures that came immediately after the Chicxulub impact, Earth's climate took another dramatic turn. As sunlight began to reach the planet again, the atmospheric conditions created by the impact set off a wave of intense global warming. With debris and ash starting to settle, sunlight returned. But the effects of the gases released during the collision and volcanic activity were far from over. The warming that followed was sudden and extreme, as gases in the atmosphere trapped heat close to the planet's surface, leading to the greenhouse effect. When the asteroid hit, it released not only debris, but also a vast amount of carbon dioxide and other greenhouse gases. the impact ignited fires across large swathes of land, releasing huge amounts of carbon into the atmosphere. Volcanic eruptions, particularly those in the Deccan Traps, were already adding carbon dioxide and sulfur compounds to the air. As a result, the atmosphere became saturated with gases that trap heat, preventing it from escaping into space. This layer of greenhouse gases acted like a blanket, capturing warmth and causing a rise in global temperatures. For ecosystems already struggling with the rapid cold that had initially followed the impact, this sudden warming added a new layer of instability and danger. Tropical forests, already devastated by fires and the lack of sunlight, found it difficult to recover in the intense heat. Plants that relied on stable temperatures and specific rainfall patterns had little chance to adapt to the sudden shift. Species that managed to hold on during the cold period now faced a different threat as their environments turned hotter and drier, leading to even more scarcity of resources. Water sources, essential for life, began to evaporate quickly, leaving plants and animals in dire need. The effects of the warming extended to the oceans, which had also been cooling during the initial phase after the impact. As the Earth heated up, ocean temperatures began to rise, disrupting marine ecosystems once more. Warmer waters meant less oxygen in the oceans, putting stress on marine species that required stable, oxygen-rich environments. Coral reefs, sensitive to even slight temperature changes, struggled to survive as the waters around them grew warmer and less hospitable. In the open ocean, fish populations dwindled as rising temperatures altered migration patterns and disrupted food availability, leaving marine life at all levels in disarray. The sudden heating also affected the polar regions, which were not immune to these changes. Ice, already reduced from the initial cold, began to melt at an accelerated rate. Glaciers and ice caps that had formed started to shrink, adding more fresh water to the oceans and altering sea levels. Rising sea levels flooded coastal areas, wiping out habitats that had only just begun to stabilize. This flooding also affected freshwater systems, as salt water pushed into rivers and lakes, making the environments inhospitable for many species that couldn't adapt to the higher salinity levels. Soil in many areas had been stripped of nutrients during the fires and acidic rains, and the intense heat made it even harder for plants to take root and recover. Without plants to stabilize the soil, erosion became a widespread issue, leading to barren landscapes. For herbivores, the lack of vegetation left few options for sustenance. Clouds, laden with particles from the impact and volcanic eruptions, trapped heat close to the surface, intensifying the warming effect. Rain patterns became unpredictable and often devastating, with intense short-lived storms drenching regions that then dried up quickly under the intense heat. Plant life, unable to establish roots in areas that alternated between drought and flood, suffered immensely. Over time, the global greenhouse effect started to ease, but by then, the damage was irreversible. Ecosystems were broken, food chains were disrupted, and the world that emerged from this extreme warming phase was one where only the most adaptable species had survived. Mammals, birds, and reptiles that could endure rapid environmental changes became the new pioneers in a world devoid of the once dominant dinosaurs. Echoes of survival, creatures that outlasted the dinosaur cataclysm. In the wake of the cataclysm that marked the end of the dinosaurs, the world had become a drastically different place. Yet, even in the ruins of a shattered environment, life persisted. Against all odds, certain creatures found ways to survive, adapting to conditions that would have been fatal to most. These survivors, small mammals, certain reptiles, birds, and even some plants, were not just lucky. Each of these groups had unique traits and behaviors that gave them the edge they needed to endure a world that had turned harsh and unforgiving. In their new, harsh reality, creatures that could tolerate drops in temperature had a clear advantage. Reptiles, for instance, tend to thrive in warm, stable climates. Without a means to regulate their body temperatures internally, many of these animals couldn't adapt to the drastic cooling that followed the asteroid impact. But small mammals and certain birds had warm-blooded physiology, allowing them to generate their own heat and withstand colder conditions better than cold-blooded animals. These animals could survive the new chill that gripped the world, even if they had to find extra food to fuel their metabolisms. Small mammals had, up to that point, been creatures living in the shadows of the larger, more dominant dinosaurs. These mammals, though seemingly insignificant, were well suited to the new world that emerged after the impact. Their small size made them less dependent on large amounts of food and shelter, allowing them to thrive on limited resources. Many of these mammals were nocturnal, a behavior that likely shielded them from the worst of the daytime heat and radiation that followed the impact. For mammals, burrowing and hiding underground were critical strategies. The debris-choked skies and extreme conditions made surface life almost impossible for extended periods. But beneath the ground, sheltered from acid rain, fire, and intense temperature shifts, mammals could find a relatively stable refuge. Underground burrows provided insulation from the cold and a buffer against falling ash, offering some protection from the poisonous fallout. In terms of diet, these small mammals also had an advantage. They were omnivorous, able to eat a range of foods including seeds, roots, insects, and small animals. As the rich and diverse plant life that had once covered Earth disappeared, mammals adapted to a patchwork of survival foods. Insects, which could also endure harsh environments, became a critical food source. With the larger dinosaurs gone, the smaller food chain stabilized, even if only temporarily, in favor of those who could adapt to scarcity. Mammals were generalists, not tied to a single food source like many larger herbivores or carnivores had been. This adaptability allowed them to find sustenance in places where more specialized animals would have perished. Beyond physical adaptations, reproductive strategies also played a part. Many small animals, especially mammals and birds, reproduce more quickly than large dinosaurs. Shorter life cycles and faster reproduction meant that surviving populations could recover more quickly than those of species that took longer to reach maturity and reproduce. Rapid reproduction allowed these animals to take advantage of any temporary relief in environmental stress, ensuring that their species endured, even if individual lifespans were shortened by the difficult conditions. Certain reptiles like turtles also managed to survive the devastation, showing remarkable resilience in the face of extreme environmental shifts. Turtles had two significant advantages: their hardy physiology and their ability to enter states of dormancy. Unlike mammals, which needed to regulate their body temperatures actively, turtles could slow their metabolism and wait out periods when food and warmth were scarce. Some species were able to go months, even years, in a semi-dormant state, reducing their energy needs and outlasting the worst phases of the extinction event. Aquatic turtles, in particular, found a level of shelter in lakes and rivers. While these bodies of water were affected by acid rain and toxic runoff, many turtles could retreat to the muddy bottoms, where conditions were more stable than on the surface. Fresh water offered these reptiles a refuge from the fires and ash that had ravaged land habitats. Much like turtles, many amphibians could retreat to aquatic environments, where conditions were somewhat less extreme. Some amphibian species possess the ability to enter a state of torpor, lowering their metabolism to survive when food is scarce. Their moist skin, while making them vulnerable to pollutants, also allowed amphibians to absorb moisture and nutrients directly from their environment, making them less dependent on external food sources. Furthermore, amphibians' life cycles often involve both water and land, giving them a level of flexibility in finding suitable habitats. They were not tied solely to either aquatic or terrestrial environments, which allowed them to navigate the changing landscape in a way few other animals could. Not all birds made it through, but the lineages that did so shared important traits that made survival possible. Smaller-bodied bird species, particularly those that could adapt their diet, had an advantage. Some early bird species likely fed on insects and small plants, diets that required fewer resources and were less vulnerable to environmental shifts than larger food sources. Their ability to fly was another important factor. Flight gave birds access to food sources that other creatures could not reach and allowed them to move to less affected areas when conditions worsened. Although the skies were often filled with ash and debris, birds could travel across larger areas in search of resources, covering distances that terrestrial animals could not. For many bird species, their adaptability in both movement and diet proved vital to survival. Many species of insects have short life cycles, meaning they can reproduce rapidly, allowing them to evolve and adapt to new conditions within just a few generations. Insects like beetles and ants, which could feed on detritus and decaying matter, found sustenance in places where other creatures could not. Their small size and ability to live in large colonies also helped insulate insect populations against the rapid changes taking place around them. Many insects could burrow into the ground, hiding until conditions improved, and they also had simple diets that allowed them to feed on decaying organic material left in the aftermath. Certain insect species are known for their resilience, and they quickly adapted to the drastic changes in the environment. Some could even endure low oxygen levels and harsh chemical conditions, making them particularly suited to survive in an Earth dominated by ash and dust clouds. Insects not only survived but likely thrived, becoming a new base for the recovering food web as they adapted to the decaying world around them. Certain hardy plant species, particularly ferns, managed to cling to life. Ferns have a unique advantage in their reproductive cycle. They spread through spores rather than seeds, which allowed them to grow rapidly when conditions improved, even in poor soil. As the climate slowly stabilized, these ferns were among the first to reclaim the barren lands, setting the stage for other plant species to eventually return. By creating pockets of green in an otherwise desolate landscape, these ferns supported the beginnings of a recovery ecosystem, attracting insects and small animals that would help disperse plant life and slowly rebuild the web of life. Freshwater fish, especially those in smaller rivers and streams, faced enormous challenges with the acid rain and pollution. However, some managed to survive by moving to less affected areas or by adapting to changes in water chemistry. Fish that could tolerate fluctuating pH levels were more likely to survive, and as conditions stabilized, they would go on to repopulate freshwater ecosystems. In the oceans, some marine life managed to hold on in deeper waters, where temperature and chemical changes were less severe than on the surface. As the years wore on, the Earth began to heal, sunlight returned, and ecosystems gradually reformed. These resilient species were there to take advantage of the renewed opportunities, filling niches left vacant by the mass extinction and diversifying as the planet continued its slow recovery. The traits that helped them survive the impact's aftermath allowed them to thrive in the new world, setting the stage for an evolutionary shift that would shape the future of life on Earth. How large size became a disadvantage. As environmental chaos swept across the planet, some of the very traits that had once made dinosaurs successful became their greatest vulnerabilities. The size that had allowed them to dominate their ecosystems turned into a severe disadvantage. Many dinosaur species were massive, towering above other life forms and requiring enormous amounts of food, water, and space to survive. In a world suddenly stripped of stability, these needs became nearly impossible to meet. Large dinosaurs were among the first to face starvation as resources grew scarce. Massive herbivores like the long-necked sauropods, which had roamed freely across lush landscapes for millions of years, depended heavily on vast quantities of vegetation. They had specialized in eating entire forests worth of leaves, branches, and plants daily. But when the Chicxulub asteroid struck and environmental conditions spiraled, plant life was among the first things to suffer. Without a reliable supply of food, large herbivores faced a devastating choice: either find a way to survive on a fraction of their normal intake, or slowly starve. But for creatures as large as the sauropods, cutting down on food wasn't an option. Their enormous bodies needed constant fuel just to stay alive. Without sufficient vegetation to graze on, these giants had nowhere to turn. Unlike smaller creatures, which could adapt by seeking alternative food sources. Sauropods and other large herbivores had evolved specifically to eat vast amounts of plant material. In contrast, smaller herbivorous dinosaurs and mammals could scrape by on what little vegetation was left. They had fewer caloric needs, could forage over smaller areas, and were less restricted in what they could eat. Some smaller animals turned to roots, seeds, and whatever remnants of plant life they could find, giving them a far better chance at surviving the sudden food shortages. But for creatures weighing tons, scavenging for scraps wasn't an option, and so they began to perish in droves as food sources disappeared. Apex predators like the Tyrannosaurus rex relied on a steady supply of prey to meet their own high-energy needs. For creatures like T-Rex, which weighed several tons and was equipped with powerful muscles and jaws built to bring down large prey, the sudden drop in herbivore populations created a crisis. Their size, strength, and speed had been perfectly suited to a world filled with equally enormous animals. But as the populations of large herbivores began to crash, the hunters found themselves with nothing to eat. Hunting smaller animals wasn't practical. These creatures wouldn't provide enough sustenance for massive predators like T-Rex to survive. The large bodies of dinosaurs also made it difficult for them to adapt to the sudden shifts in temperature and environment. Large animals have slower metabolisms relative to their size, which can be an advantage in stable climates, but is a disadvantage when conditions change rapidly. When the Earth cooled suddenly in the aftermath of the impact, large dinosaurs couldn't quickly adjust to the drop in temperature. Smaller animals, with their faster metabolisms, could generate body heat more easily and seek out warmth in smaller shelters or burrows. For large dinosaurs, however, taking cover wasn't an option. They were too big to hide from the cold and lacked the insulation or fat reserves that might have helped them endure. They were exposed to the elements and unable to regulate their body temperatures, making survival even harder. Large dinosaurs also had long growth cycles. For a creature like the sauropod, reaching full size could take many years, even decades. This slow development made it difficult for dinosaur populations to recover after a sharp decline. In contrast, smaller animals, which reproduced quickly and in greater numbers, could recover more rapidly after population crashes. For dinosaurs with long reproductive cycles, surviving depended on a stable world, one where they could grow slowly, reproduce over many years, and find plentiful food supplies. But in the unstable conditions following the impact, there was no such stability to rely on. As large populations dwindled, there weren't enough new individuals being born to replace them, leading to population collapse over a relatively short span of time. The physical limitations of large dinosaurs also meant that they were slow to migrate. Moving a massive body across a vast area required both energy and resources, something that had been feasible in a world of abundant food and water. But with habitats suddenly fragmented and resources scarce, migrating became a monumental task. Large dinosaurs couldn't simply pick up and move to a new area in search of food or water. Their size and energy demands tied them to specific regions. When these areas could no longer support them, they were effectively stranded. Their physical scale became an anchor, rooting them in dying ecosystems from which they couldn't escape. Large dinosaurs, particularly herbivores, often traveled in herds or family groups. While this behavior had once provided protection and improved their chances of finding food, it now became a hindrance. In an environment stripped of resources, staying in large groups increased competition for what little food remained. Many large herbivores were highly social, moving together in herds that required vast feeding grounds. Now, in the post-impact world, there were no longer vast plains of vegetation to support them. Herd dynamics became a burden rather than a benefit, leading to more rapid declines within these groups as food grew scarcer. In the grand scheme of evolution, large size had been one of nature's boldest experiments. For millions of years, it had been a successful strategy, allowing dinosaurs to dominate their ecosystems and access resources that smaller creatures couldn't reach. But as the asteroid impact brought environmental instability, large dinosaurs found themselves trapped by their own biology, unable to adapt quickly enough to survive the rapid changes that unfolded around them. Unseen killers, bacterial blooms, and marine life collapse. As soot and ash from fires covered the surface of the sea, light was blocked from penetrating the water. Without sunlight, the photosynthetic plankton at the ocean's surface began to die off rapidly. These plankton formed the base of the marine food chain, so their disappearance sent a ripple through ocean life, impacting creatures of every size. But beyond this visible breakdown, an invisible shift was also happening in the ocean's delicate chemistry, giving rise to dangerous bacterial blooms. When the impact's fallout settled, ocean waters became filled with minerals and nutrients leached from decaying organic material, debris, and other chemicals that had fallen from the atmosphere. These nutrients, while essential in balanced quantities, began to feed explosive growth in certain bacterial species. As these harmful bacteria proliferated, they began to dominate the oceans, feeding on the abundant nutrients left behind. In normal conditions, the balance between marine bacteria and other microscopic life forms keeps the ocean's ecosystem stable. But as these harmful bacteria grew out of control, they consumed oxygen in the water, causing large sections of the ocean to turn into dead zones with dangerously low oxygen levels. These dead zones became hostile environments for fish and other marine animals, who struggled to breathe as oxygen levels plummeted. The sudden loss of oxygen in ocean water forced many sea creatures to migrate or perish. Fish, shellfish, and other marine organisms began to die off en masse, unable to escape from the suffocating water. As their bodies decayed, they added more nutrients to the water, further feeding the bacterial blooms and worsening the cycle. This increase in bacterial activity released additional harmful compounds, like hydrogen sulfide, into the water and air, poisoning the already fragile ecosystems. Hydrogen sulfide, a toxic gas, could kill marine animals exposed to it and even threaten coastal life if it escaped into the atmosphere. Coral reefs and other sensitive habitats were particularly vulnerable, as they depended on clear, stable waters and oxygen to thrive. Coastal regions, where rivers and streams emptied into the ocean, were filled with runoff containing ash, debris, and other materials left by fires and decaying plants. This nutrient-rich runoff further encouraged bacterial blooms near shorelines. These coastal areas, often home to many juvenile fish, invertebrates, and plants, became zones of decay rather than life. Fish populations that depended on these coastal nurseries for reproduction found fewer safe places to spawn. Shoreline plants, like mangroves and seagrasses, were also affected, as they faced nutrient overload and were starved of the oxygen needed to maintain their growth. Algae, another group of organisms that thrives on nutrient-rich waters, also bloomed uncontrollably. Some algae produce toxins harmful to fish and marine mammals, especially when they appear in high concentrations. As these algal blooms spread across the oceans, they released toxins that further reduced fish populations and harmed marine mammals and birds that consumed contaminated fish. Seabirds, which relied heavily on fish for food, faced starvation as fish populations crashed or became toxic. The algal blooms created an additional barrier to recovery for the oceans, as they limited the ability of marine life to re-establish itself. Marine ecosystems are interconnected with terrestrial ecosystems through animals like seabirds and coastal predators that feed in the ocean and return to land. As marine species began to die off, animals like seabirds and other shoreline hunters were left with limited food sources, and many either starved or migrated in search of new feeding grounds. The disappearance of fish and other sea creatures affected entire populations of seabirds, some of which relied exclusively on marine life to survive. These birds, already weakened by the initial cold and dark, could not find enough food to sustain their populations, and many species, faced drastic population drops or local extinctions. The collapse of fish stocks in shallow waters forced marine mammals, like seals and small whales, to compete for limited food resources. The energy costs of finding food increased, and weakened animals became more vulnerable to disease and starvation. As marine mammals struggled to survive, their deaths added further nutrients to the water, perpetuating the cycle of decay and further encouraging bacterial and algal blooms. Over time, as oceanic chemistry stabilized and nutrient levels fell, some semblance of balance began to return. However, the effects of the blooms and the breakdown of marine food chains left long-lasting scars on ocean life. Entire populations of fish, coral, and marine mammals had been decimated, and ecosystems that once thrived in biodiversity were left impoverished. The survivors were often species that could tolerate low-oxygen environments or live off of the decaying material, such as certain types of bacteria and detritivores. But these organisms could not replace the diversity and ecological complexity that had been lost. While the terrestrial landscape of Earth eventually healed as sunlight returned and new plant growth began, the oceans faced a slower recovery. Without sunlight to drive photosynthesis for extended periods, ocean ecosystems had lost a core energy source, one that would take far longer to re-establish. The bacterial and algal blooms faded, but the gaps in the food chain remained, with many species unable to recover to their former numbers. Fish populations, for instance, took many generations to rebound, especially without the rich plankton populations that had once supported their growth. Coral reefs, once vibrant centers of ocean life, had vanished in many places, reducing the biodiversity of entire regions. The collapse of the marine ecosystem also reshaped Earth's atmosphere and climate. Marine life plays a significant role in regulating global carbon levels, as plankton absorb carbon dioxide during photosynthesis. With fewer plankton, the carbon cycle slowed, leading to further imbalances in atmospheric gases. A shattered world. What life was like for survivors on the ground. In the bleak aftermath of the asteroid impact, life on Earth was left to pick up the pieces in a world that bore little resemblance to what had come before. The sky was hazy with dust that had not yet settled, and the ground was scattered with ash and remnants of charred vegetation. Survivors, from small mammals to resilient plants, faced a landscape stripped of the rich ecosystems that had once flourished. In this early stage of recovery, the plants that survived were limited in type. Unlike the forests of the past, these new landscapes lacked diversity. There were few flowering plants or tall trees, as these required more stable conditions and consistent light to grow. Forests were gone, leaving open stretches dotted with patches of resilient vegetation. The world felt like a single-layered environment, stripped of the vertical complexity that had once defined it. Small mammals began to venture out in search of food. These creatures, mostly insectivores or scavengers, made do with whatever they could find, whether it was edible remnants of plants, insects, or the carcasses of other animals that had succumbed to the harsh conditions. For these survivors, adaptability became a lifeline. Scavenging became common as these small survivors scoured the landscape for anything that could provide sustenance. Without the competition of larger animals, these smaller predators could hunt or scavenge with greater freedom, though they were still limited by the scarcity of prey. Some early mammals took on a more active role in hunting insects and other small creatures, learning to use the low plant cover for stalking. Detritivores, which consumed dead organic material, took advantage of the abundant remains scattered across the earth. With limited sunlight, some insect species relied on decaying plants and animals as their primary food source, playing a crucial role in breaking down these materials and returning nutrients to the soil. Beetles, ants, and other scavenging insects multiplied as they fed on the remains left behind by the mass extinction. Their activity enriched the soil, slowly creating an environment more suitable for plant life to take root and grow. Food chains became simplified. Ecosystems that had once included layers of plants, herbivores, and predators were reduced to basic interactions among survivors. The absence of large dinosaurs allowed some animals to occupy new spaces, but these roles were incomplete and rudimentary compared to the complex ecosystems that had existed before. The Earth's fauna was limited, and species interactions remained simple, as the once vibrant tapestry of life was now a bare and broken outline. Some reptiles, like turtles and crocodiles, managed to persist, but even their survival was tenuous. Crocodiles survived by relying on their opportunistic hunting skills and the ability to consume almost anything that came their way. These animals, though fewer in number, continued to inhabit rivers and lakes, which offered some protection and stable conditions compared to the harsher land environments. By surviving in water, crocodiles and other aquatic animals faced less direct competition from land animals and found refuge in habitats that had retained some of their pre-extinction features. Birds, descendants of smaller theropod dinosaurs, became crucial survivors in this barren landscape. Over time, they began to diversify, finding new ways to adapt to the altered environment. Some developed specialized diets or behaviors that allowed them to thrive in specific niches, such as feeding on the abundant insects that had taken over much of the land. With fewer large predators, certain bird species expanded into these new spaces, gaining a foothold in ecosystems where competition was limited. As vegetation began to recover and spread, ground cover provided more stable habitats for mammals and birds to establish territories. This new plant life, though slow-growing, allowed small herbivores to find food more reliably, helping populations to increase gradually. Mammals expanded their numbers in response to the improving conditions. Some began to form social groups or develop behaviors suited to foraging in the increasingly dense plant cover. In areas where water was available, early wetlands began to form as plant life helped stabilize soil and prevent erosion. Wetlands attracted various species of birds and insects, creating small localized centers of life in the otherwise barren landscape. These wetlands supported food chains based on small plants and aquatic insects, offering a refuge for species that had adapted to moist environments. Though modest, these wetlands played an essential role in seeding new life and adding diversity back into the world. Gradually, small ecosystems took root, forming pockets of resilience where plants, insects, mammals, and birds could begin to interact in more complex ways. Food chains grew in these scattered locations, with herbivores and small predators finding reliable resources within the patches of vegetation. These early ecosystems were still fragile, but they marked the beginnings of a slow recovery as life adapted to the transformed Earth. Over generations, plants developed deeper root systems, stabilizing the soil and creating more dependable habitats. As the dust in the atmosphere began to settle and sunlight slowly returned, plant growth accelerated, and the world started to regain some of its lost diversity. The warming climate, combined with the steady increase in sunlight, allowed for taller plants and shrubs to develop, leading to the reappearance of more complex vegetation. Herbivores now had more food sources, and predators began to grow in number as prey became abundant. The slow process of ecological succession reshaped Earth into a place that, while different from the world of the dinosaurs, was once again vibrant with life. When dinosaurs truly disappeared, the final days of stragglers. Some scientists believe there is evidence suggesting that, in isolated regions, small populations of dinosaurs may have lingered for a short while after the asteroid's initial impact, holding on in pockets where conditions allowed them temporary refuge. These stragglers would have been shadows of their former selves, creatures once dominant but now on the edge, forced to live in landscapes stripped of the resources they had relied on for millions of years. Many of these dinosaurs were highly specialized, each species adapted to particular diets, climates, and even social structures that would have broken down under the stress of the new world. In this changed landscape, the dinosaurs faced the brutal reality that there were few places left where they could thrive. Evidence of dinosaur survival beyond the impact itself is limited, but some fossils and sediment records indicate that small dinosaur populations could have existed briefly after the mass extinction event. This evidence is scattered and indirect, but in areas where conditions may have been more sheltered, such as river valleys, caves, or coastal inlets, it is possible that certain species managed to linger. Their survival, however, would have been tenuous. These populations, once spread across vast territories, were now likely isolated, cut off from other groups and the wide-ranging habitats they had once claimed. Isolation may have briefly provided some protection, but it also meant that these small groups were more vulnerable to even slight changes in food availability, temperature, or predation pressures from species adapting more effectively to the new environment. In this final struggle for survival, some dinosaur species may have attempted to adapt by altering their behavior or diet, but adaptation is a slow process. Many dinosaurs were unable to shift quickly enough to match the rapid and extreme environmental changes. Some scientists theorize that the flexibility seen in certain smaller bird-like dinosaurs, which eventually evolved into modern birds, may have been what allowed some of their relatives to survive. However, for most non-avian dinosaurs, flexibility and adaptability were insufficient to keep up with the unyielding pressures they faced. While some dinosaurs might have clung to life in scattered regions, these populations would have been so small and disconnected from one another that they lacked the diversity needed to recover or reproduce at sustainable levels. As each isolated group dwindled in numbers, the genetic variety necessary for long-term survival would have also diminished. The smallest remaining groups, though perhaps capable of holding out for a short while, would have been left vulnerable to any additional stress, be it a particularly cold night, a lack of food in one season, or the simple aging and death of the remaining individuals. As conditions continued to change, some of the very last dinosaurs may have attempted to scavenge where they could, feeding on plant remnants or small animals that survived in even smaller numbers than they did. For species that once had access to a complex ecosystem filled with food, shelter, and water, the scarcity of their new reality would have been profoundly difficult. Fossil records suggest that, in some cases, signs of starvation and malnutrition appear in the bone structures of certain dinosaurs from this time. These last dinosaurs lived lives far removed from the relative abundance and dominance their species had enjoyed for millions of years. As the days, months, and years passed, the last dinosaurs would have faced relentless pressure from every angle: starvation, isolation, and the unyielding forces of a planet transformed by catastrophe. With each passing generation, their numbers shrank, and the few that remained struggled in ways that were in stark contrast to the lives of their ancestors. These final dinosaurs, the last remnants of a once great dynasty, gradually disappeared as the limitations of their biology and the unforgiving environment sealed their fate. Dinosaurs in the DNA of ecosystems, their impact on plants and soil. For millions of years, dinosaurs influenced plants, soil composition, and the cycles of nutrients that supported entire landscapes. Herbivorous dinosaurs, which included some of the largest animals to walk the earth, had an enormous appetite for vegetation. They consumed massive quantities of plant material daily, browsing and grazing across forests, plains, and floodplains. By doing so, these herbivores controlled the distribution and growth of certain plants, preventing any single species from overwhelming an area. Their constant movement from place to place created opportunities for new plants to take root, encouraging diversity in plant life. When these animals fed on plants, they often ingested seeds, which would pass through their digestive systems and be deposited in new locations. This natural process of seed dispersal allowed plants to spread across vast distances, enhancing genetic diversity and supporting healthy populations of plant species. By moving seeds far from their parent plants, dinosaurs helped to establish new plant populations, supporting forest regeneration and the development of diverse ecosystems. Insects, fungi, and other decomposers thrived in dinosaur-rich environments, breaking down waste and contributing to the soil's health. These organisms relied on the organic material left behind by dinosaurs, creating micro-ecosystems where nutrients were recycled and returned to the soil. Some dinosaurs, particularly those with large claws and powerful limbs, also influenced the soil through their physical activities. As they moved through forests and plains, digging, scraping, and sometimes even building nests, they disturbed the ground, loosening the soil and allowing for the aeration of the earth. This process helped water and air to penetrate the soil more easily, supporting root growth and promoting plant health. By turning the soil over, dinosaurs helped to prevent soil compaction, which can stifle plant growth and reduce the availability of nutrients. The large size of dinosaurs meant that their impact on plant life was often felt on a large scale. In some cases, forests and plains were shaped by the presence of herds of large dinosaurs moving through the landscape. Trees and plants adapted to withstand the physical pressures of being grazed upon, and some species even developed defenses such as thorns, tough leaves, or chemical deterrents to protect themselves from herbivores. These adaptations, in turn, influenced the types of dinosaurs that could feed on them, creating a cycle of co-evolution where plants and herbivores shaped each other over millions of years. Carnivorous dinosaurs, though not directly involved in grazing or seed dispersal, also contributed to the structure of ecosystems. Predators played a crucial role in controlling herbivore populations, preventing overgrazing and allowing plant life to regenerate. By hunting herbivores, carnivores helped to maintain a balance within ecosystems, ensuring that plant life could recover and continue to support diverse animal populations. This balance allowed ecosystems to sustain a variety of life forms, from tiny insects to the largest dinosaurs, creating a stable environment where species could thrive. When these dinosaurs eventually disappeared, the ecosystems they had shaped for millions of years experienced a profound shift. Without the daily activities of large herbivores, certain plants may have spread unchecked, while others lost their primary means of seed dispersal. The nutrients that had been cycled through the landscape in such large quantities now diminished, as there were no longer massive animals to consume, digest, and redistribute organic matter across vast distances. This sudden loss of both animal and plant life left an ecological gap, as smaller animals could not immediately replace the roles that dinosaurs had fulfilled. In the absence of these giants, the natural balance of ecosystems had to be re-established from scratch, a slow and gradual process that opened the door for new species to rise in prominence. In the wake of giants, the rise of mammals. No longer forced to live in the shadows of gigantic dinosaurs, mammals found themselves freed from intense competition with large, dominant creatures. The new open niches on land, in trees, and even in the water provided spaces for different types of mammals to survive, experiment, and evolve into a variety of forms and sizes. This was the beginning of an evolutionary journey that would shape the world for millions of years to come. Before the asteroid impact, mammals had been relatively small, often no larger than a modern raccoon or small fox, and they mostly lived as nocturnal or burrowing creatures. Their small size and secluded habits helped them survive in a dinosaur-dominated ecosystem, but it also limited their ability to grow and diversify. With the dinosaurs gone, mammals faced an empty environment ready to be filled. There were few large predators, no massive herbivores, and no high-reaching feeders. The first major change among mammals came with the emergence of different diets. With the death of the large, plant-eating dinosaurs, there was an abundance of vegetation available, and some early mammals adapted to fill this role. Certain species developed into herbivores, able to digest tough plant material and browse on the remaining leaves, roots, and grasses covering the land. These herbivorous mammals varied in shape and size, some growing large enough to graze on bushes and shrubs, while others stayed small, feeding on low-lying vegetation. Early mammalian carnivores emerged, some of which adapted to hunt the smaller mammals, reptiles, and birds that began to populate the post-dinosaur landscapes. These early predators were not large at first, but they were fast and effective, using sharp teeth and claws to catch prey. As ecosystems developed and food chains became more complex, these carnivorous mammals diversified into various roles, from small, quick hunters to larger, ambush predators. Forests provided both shelter and food, and mammals began to evolve with characteristics suited for life among trees. These tree-dwelling or arboreal mammals developed strong limbs and prehensile tails, allowing them to swing and move through the trees with ease. They became experts at climbing, a skill that helped them find safety and food above the ground. Living in trees also provided a way to avoid land-based predators, as these early mammals could escape danger by moving into the branches. With time, mammals also ventured into open grasslands, which started to expand as forests gave way to drier climates. These open spaces were ideal for grazing mammals that could feed on the grass. And soon, animals began to evolve with longer legs and faster speeds to cover large areas in search of food. The animals that thrived in these grasslands would later become some of the first large herbivores, ancestors of creatures like antelopes, bison, and horses. Speed became an important trait in these environments, both for escaping predators and for moving efficiently to find fresh grazing grounds. This shift marked an important step in mammalian evolution, as the need for speed and endurance brought about new body shapes and sizes, further differentiating these animals from their ancestors. Early aquatic mammals took on a variety of different forms, with some developing webbed feet or powerful tails to help them move efficiently in water. Over time, these mammals would give rise to marine species, such as whales, dolphins, and seals, which evolved to live their entire lives in the ocean. This transition from land to water opened yet another path for mammals, leading to one of the most dramatic adaptations in the history of life on Earth. Over millions of years, as the ecosystem stabilized and climates shifted, mammals continued to diversify, filling roles in every part of the environment. This period saw the evolution of several unique features that allowed mammals to thrive. One of the key advantages mammals had was their ability to regulate body temperature. This allowed them to live in a wider range of environments, from cold, mountainous regions to warm, humid jungles, without depending on the sun for warmth. This adaptability enabled mammals to occupy habitats that may have been inaccessible to other types of animals. The reproductive strategy of mammals also contributed to their success. Unlike many dinosaurs that laid eggs, most mammals gave birth to live young, which allowed them to provide better protection and care to their offspring. Mammalian mothers often nurture their young for extended periods, teaching them survival skills and giving them a better chance at survival in the wild. This parenting style created strong social bonds within groups and increased the survival rate of young animals. Some mammals, like certain species of rodents and primates, also began to form family groups and social structures, which provided added protection from predators. Over time, mammals with large bodies, like the ancestors of elephants, rhinos, and hippos, began to appear. These animals adapted to eating massive amounts of vegetation and required large areas of land to support their needs. They evolved thick skins, tusks, and other features to protect themselves from predators and harsh environments. With these large body sizes came new challenges, but it also gave these animals the ability to defend themselves and dominate certain environments. Meanwhile, other mammals evolved smaller, more specialized forms, giving rise to a wide array of creatures with different diets, habitats, and behaviors. Rodents, with their sharp, gnawing teeth, became adept at eating a variety of foods, from seeds to roots. Bats, with their unique ability to fly, took to the skies, filling a niche that had been left empty since the extinction of flying reptiles. Primates began to develop more complex behaviors and larger brains, setting them on a path that would eventually lead to the emergence of humans. Through these varied adaptations, mammals became one of the most diverse groups of animals on Earth. They thrived not because they were the largest or strongest, but because they were adaptable, resourceful, and resilient. In the wake of the dinosaurs' extinction, the ability to change and survive in different environments proved to be a powerful advantage. As ecosystems continued to evolve, mammals shaped and reshaped themselves to fit into every possible niche. How avian dinosaurs defied extinction. Among the vast lineage of dinosaurs that once ruled the Earth, only one group managed to defy extinction, the avian dinosaurs, which we now know as birds. As the mass extinction wiped out the towering, fearsome, and diverse dinosaur groups, birds somehow adapted and endured, continuing the legacy of their ancient ancestors. Their survival was no small feat, as they faced the same devastating changes to the environment that eradicated most other life forms. Long before the asteroid struck, birds had already evolved certain traits that likely contributed to their survival. Among these was their smaller size compared to many other dinosaurs, which meant they required fewer resources. While the massive dinosaurs depended on large quantities of food and vast territories, birds could get by with less. They had lightweight, hollow bones, an adaptation that allowed for flight, but it also gave them an advantage in energy efficiency. With fewer demands for food, space, and resources, they were better suited to survive in a world where food became scarce. With wings to carry them, they were highly mobile, able to escape from hazardous areas and search for food over wider territories. They could leave barren areas and search for small pockets of habitable land where life still clung on. In a sense, their wings gave them an escape route that most other animals did not have. This mobility also opened up more feeding opportunities, as they could scavenge from carcasses, find seeds or insects, and search for food in areas that were less impacted by the disaster. Unlike some dinosaurs that specialized in one type of food, birds displayed a range of feeding behaviors from insect eating to scavenging and seed eating. Some species could switch between food sources as conditions required, a trait that became essential when regular sources of food disappeared. The variety in bird beaks allowed them to exploit a range of food sources. For instance, some birds had sharp, hooked beaks for tearing into meat, while others had pointed beaks perfect for picking up insects or seeds. This specialization allowed them to access different types of food and ensured that certain bird species could survive by filling various ecological roles. The digestive systems of birds were also highly efficient, which helped them make the most of the food they did find. Birds digest food quickly, allowing them to stay active and maintain high energy levels. Their efficient metabolism supported their fast-paced lifestyles, which became even more critical in a world where survival often depended on the ability to move quickly, escape predators, and cover vast distances to find food. Additionally, their efficient metabolic systems required them to be warm-blooded, meaning they could generate their own heat. Many bird species use secluded areas for nesting, such as trees, cliffs, and ground burrows, which protected their young from predators and environmental hazards. By hiding in hard-to-reach areas, they could protect their eggs from the harsh conditions on the ground and shield their offspring from hungry scavengers. For those birds that nested in trees, this meant escaping certain dangers on the ground, while ground-nesting birds often burrowed or hid their nests to reduce exposure. Birds also have relatively short reproductive cycles, with many species able to lay multiple eggs in a single season. Unlike large dinosaurs that may have had long gestation periods and fewer offspring, birds could quickly increase their population numbers, even if some nests were lost to predators or environmental threats. The ability to lay many eggs and raise young at a fast pace meant that bird populations could rebound more swiftly, even after devastating losses. Birds have a capacity for learning and adapting to new situations, traits that were particularly useful in a post-impact world full of dangers. They could adapt their nesting sites, change their migration patterns, and modify their feeding habits to suit new and unpredictable conditions. This behavioral flexibility allowed them to test out different strategies and persist in difficult environments. Over time, birds began to spread across the planet, occupying forests, mountains, plains, and even islands. Some developed migratory patterns, moving between regions to follow food sources and favorable climates. Others settled in specialized habitats, evolving unique traits suited to their new homes. The surviving birds continued to evolve and diversify, branching into countless forms that would eventually lead to the vast variety of bird species we see today. Bloodlines that survived. Traits of dinosaurs found in birds today. Birds may look and act like their own distinct branch of life today, but beneath their feathers, they carry many of the same traits that once defined their dinosaur ancestors. As scientists continue to uncover more fossil evidence and study bird anatomy and behavior, it becomes clear that these traits didn't just vanish with extinction, they evolved, passing from one generation to the next and living on in today's avian species. The presence of feathers is perhaps the most well-known link between modern birds and their dinosaur ancestors. Fossils of dinosaurs like Archaeopteryx and other feathered theropods have shown that feathers were not exclusive to birds. They were also present in many non-avian dinosaurs. Feathers likely evolved for reasons other than flight, serving initially for insulation, camouflage, or even display. In some species, brightly colored or patterned feathers may have played a role in attracting mates or intimidating rivals. This trait was passed down to birds, which took these early feathers and evolved them into specialized forms for flight, warmth, and social signaling. Birds display complex social behaviors, communicate through vocalizations, and often exhibit high levels of parental care. These behaviors likely have roots in dinosaur life, as fossil evidence suggests that some dinosaur species nested in groups and may have cared for their young. For instance, the fossilized remains of certain dinosaurs have been found in what appear to be carefully arranged nesting grounds, suggesting that they returned to specific locations to lay their eggs and may have protected them as they developed. Today, similar nesting behaviors are seen in birds, from ground nesting species like penguins, which huddle together for warmth, to cliff dwellers like swallows, which build nests in safe, sheltered spots. Many theropod dinosaurs, including Velociraptor, had a unique type of joint in their hips that allowed for a range of motion similar to the one birds use for walking and running today. In birds, these joint adaptations were further refined, allowing for the smooth, balanced gait that makes flight possible. In a way, every time a bird walks, runs, or hops, it mimics the movements of its ancient relatives. The bird's unique breathing system is another example of dinosaur legacy in modern avian species. Unlike mammals, which have lungs that fill and empty with each breath, birds have a more efficient respiratory system with air sacs that allow for a continuous flow of oxygen. This setup helps them extract more oxygen with each breath, an adaptation necessary for the energy demands of flight. Evidence suggests that similar air sac systems were present in some large theropods, which likely required a highly efficient respiratory system to fuel their active lifestyles. Even the way birds hatch from eggs shows a connection to their dinosaur past. Fossilized dinosaur eggs reveal similar shell structures and incubation practices to those seen in birds. Some dinosaurs may have even used their own body heat to warm their eggs, much like birds do today. Fossils showing adult dinosaurs positioned over nests, covering their eggs with their bodies, suggest that these creatures engaged in behaviors that resemble brooding. Although modern birds don't usually rely on claws for hunting or defense as many dinosaurs did, they still retain the remnants of these tools. For instance, some birds, like eagles and hawks, have sharp talons adapted to grasping and tearing prey, a direct link to the predatory lifestyles of their dinosaur ancestors. Other birds, like the hoatzin, even have clawed wings as chicks, which they use to climb in trees, a fascinating reminder of a more primitive stage in avian evolution. Many dinosaurs, particularly those that hunted other animals, relied heavily on keen vision to track and capture prey. Modern birds have some of the most advanced eyesight in the animal kingdom, with hawks and eagles capable of spotting prey from great distances. The eyes of birds are highly specialized, giving them the ability to see a broad spectrum of colors and detect movement with incredible accuracy. Paleontologists have uncovered fossils with preserved pigment structures that suggest some dinosaurs had vibrant colors, patterns, or even iridescent scales. This discovery shows that dinosaurs might have used color to communicate, attract mates, or blend into their surroundings. Today, birds use color in much the same way. The vibrant feathers of a peacock or the subtle camouflage of a nightjar continue the tradition of visual adaptation that began long before birds took flight. Fossilized moments. What remains in the sediment of time? In the ancient rocks that make up Earth's surface, some fossils emerge as rare windows into moments long past, capturing dinosaurs in extraordinary detail. Unlike typical fossils, which usually preserve only bones and teeth, these rare finds can reveal soft tissues, skin impressions, and even the last moments of a creature's life, frozen in stone. Fossils like these give us a glimpse of dinosaurs as they truly were, not just skeletons, but living, breathing animals, complete with scales, muscles, and expressions. For most creatures, death is followed by the quick breakdown of soft tissues as microbes, scavengers, and the elements take over. But under rare conditions, such as rapid burial in fine sediment, an oxygen-poor environment, or mineral-rich waters, soft tissues can escape immediate decay, allowing impressions to survive for millions of years. These fossils are precious to scientists because they provide details that skeletal remains alone cannot, from the texture of a dinosaur's skin to the shape of its muscles, and even hints about its last actions before it died. One famous example of such preservation is the fossil of the sun-core nodosaur, an armored dinosaur that was discovered with its skin and some soft tissue remarkably intact. Found in Alberta, Canada in 2011, this fossil dates back around 110 million years and was buried in what was once an ancient seabed. The nodosaur's body was covered in bony plates, and these were still arranged across its back as they would have been in life, providing clues about how its armor functioned and the roles it played in its survival. Even more incredible, the skin on its face and limbs remained, showing the patterns and texture of its scales, giving paleontologists the rare chance to study the surface features of a dinosaur's skin in fine detail. Unlike bones alone, this fossil showed how the animal might have looked in life, how its armor blended with its skin, and how it could have moved within its protective shell. In some cases, these fossils even capture the outlines of muscles and tendons, giving paleontologists insight into how these creatures might have moved. The nodosaur's remains, for instance, showed not only where its muscles attached to the bone, but also the thickness and arrangement of those muscles. With this level of detail, scientists can reconstruct movements, speculate on its speed, and assess how it might have defended itself or foraged for food. By analyzing these details, paleontologists can make educated guesses about how the nodosaur's body shape and muscle structure affected its behavior, whether it preferred slow, steady movement or had bursts of speed when threatened. Another exceptional find comes from the deserts of China, where fossils of feathered dinosaurs have been uncovered. These creatures, like Sinornithosaurus and Microraptor, were preserved so well that even delicate feathers, often considered too fragile to fossilize, were visible. These feathered fossils provide essential information about how feathers evolved. Many of these early feathers lacked the complex structure seen in modern birds, suggesting they may have initially evolved for warmth or display rather than flight. The fossilized feathers also preserved different lengths and patterns, hinting at a range of functions, from attracting mates to insulating against the cold. One of the most famous feathered dinosaur fossils is that of Archaeopteryx, discovered in the fine-grained limestone of Germany. This fossil is often considered the missing link between non-avian dinosaurs and birds because it has both dinosaur and bird-like features. Archaeopteryx had teeth, claws, and a long bony tail, but it also had wings and feathers similar to those of modern birds. The preservation of its feathers, particularly on its wings and tail, suggests that it might have been capable of gliding or limited flight. By studying these feathers under microscopes, scientists have been able to discern fine details, like the barbs and barbules that help feathers lock together, providing structural support for flight. Each feather's shape and positioning tell a part of the story of how flight in birds may have originated. Occasionally, fossils preserve clues about a dinosaur's diet. Fossils of herbivorous dinosaurs, like the hadrosaur Edmontosaurus, have been found with remnants of their last meal preserved in their stomach cavity. This fossilized plant matter can tell scientists what kinds of plants were part of its diet, how it digested its food, and even provide insights into the ecosystem it inhabited. By examining the types of plants found with these fossils, paleobotanists can reconstruct ancient environments, piecing together the climate, vegetation, and other life forms that coexisted with the dinosaurs. Some fossils even capture what might have been moments of death, where two or more animals are preserved together, appearing to be in the midst of a struggle. One well-known example is a fossil from Mongolia that shows a velociraptor locked in combat with a protoceratops. The velociraptor's sickle-shaped claw is embedded in the protoceratops' ribcage, suggesting that the two may have been caught in a sandstorm or other rapid burial event while fighting. This rare fossil provides a glimpse of the interactions between predator and prey, showing just how fierce survival was during the age of the dinosaurs. Tracks found in soft sediments that later hardened into rock capture moments in a dinosaur's daily life, showing its gait, speed, and sometimes even the presence of a herd. Trackways found in Wyoming show the footprints of multiple individuals from the same species moving together, indicating possible herd behavior among some types of dinosaurs. In one set of tracks, scientists observed the footprints of both adult and juvenile dinosaurs moving side by side, hinting at a form of parental care or family structure. How dinosaurs shaped Earth's history. Dinosaurs lived for over 160 million years, leaving their mark not only in the fossil record, but also in the very landscapes and ecosystems of Earth. These massive creatures had a profound influence on the world around them, shaping plant evolution, altering the structures of ecosystems, and even contributing to the geology of certain regions. Their presence changed the way life on Earth evolved, creating lasting impacts that would ripple across millions of years, long after they disappeared. During the age of dinosaurs, plant life was undergoing a significant transformation, with early forests of ferns, cycads, and conifers giving way to flowering plants in the later periods of dinosaur evolution. By feeding on vast amounts of vegetation, these large herbivores helped shape plant communities, influencing which species thrived and spread. As they fed, they likely played a role in the dispersal of plant seeds, trampling some areas and allowing different plant types to gain a foothold. Over time, the rise of flowering plants, or angiosperms, changed the landscape even more. Flowering plants are generally more efficient in reproduction and growth than their predecessors, and their spread throughout ecosystems was partly encouraged by the presence of herbivorous dinosaurs that helped disperse seeds through their movements and digestion. This evolution of flowering plants created new opportunities for insects and small animals, leading to complex food webs that would shape ecosystems long after the dinosaurs. By the time the dinosaurs disappeared, the diversity of flowering plants had established itself in many ecosystems, creating a legacy of plant evolution that would continue to impact future environments and the species that inhabited them. As top predators, large carnivorous dinosaurs like Tyrannosaurus rex and Allosaurus occupied the highest levels of the food chain, preying on other dinosaurs and smaller animals. This predator-prey relationship created a balance within ecosystems, influencing which species could survive and thrive. In ecosystems dominated by these massive creatures, smaller species had to adapt to avoid predation or find niches that would reduce their competition with larger animals. This need for survival led to evolutionary changes, as prey animals developed specialized adaptations to escape or hide from their predators. Early mammals had to develop unique traits to coexist with these larger reptiles. As small, often nocturnal creatures, early mammals developed keen senses and specialized diets, allowing them to survive in a world dominated by dinosaurs. These adaptations would later serve them well in the post-dinosaur world, setting the stage for the evolution of more diverse and complex mammalian life. In the marine environment, dinosaurs indirectly influenced life by contributing to nutrient cycles when they died near water sources. Although marine reptiles like ichthyosaurs, plesiosaurs, and mosasaurs ruled the oceans rather than true dinosaurs, the presence of both marine reptiles and terrestrial dinosaurs created complex ecosystems where nutrient cycles were intertwined. For example, when large dinosaurs died and their remains were carried into rivers and oceans, nutrients were released into the water, supporting algae growth and attracting other aquatic life. These nutrient cycles would have a lasting effect on marine ecosystems, sustaining fish and other marine creatures that would later evolve into the diverse oceanic life we see today. In the skies, flying reptiles known as pterosaurs shared the environment with avian dinosaurs or early birds. As the first vertebrates to master flight, pterosaurs occupied a range of ecological roles, from fishing near water bodies to scavenging on land. The presence of both pterosaurs and birds created a dynamic ecosystem in the skies, where competition and adaptation were constant. These flying reptiles and early birds shaped the evolution of flight, influencing how future avian species would evolve after the dinosaurs' extinction. What extinction means for us. Lessons from a lost age. Before we take a look at if we could ever resurrect dinosaurs, let's understand what the extinction means for us. Dinosaurs lived through millions of years of changing landscapes and climates, but in the end, a sudden and severe shift was enough to unravel life as they knew it. Today, as the planet faces its own set of ecological and climatic challenges, we can gain valuable insights into the importance of biodiversity, conservation, and the potential consequences of human-driven changes to the Earth's climate. In the time before the impact event, dinosaurs, plants, small mammals, and other animals existed in a relatively stable environment, where resources and habitats were abundant enough to support a variety of life forms. When the asteroid hit and triggered rapid changes, this interwoven web started to unravel as one shift in the environment impacted the species relying on it, leading to cascading effects across the ecosystem. For humans today, this interconnection is a reminder of how fragile life on Earth can be when ecosystems are put under sudden or intense stress. As climate change progresses, species and habitats around the world are already beginning to feel the effects. Animals that rely on specific temperatures, water sources, or food availability face challenges as these conditions change. When the extinction event wiped out so many species, the ecosystems that survived were vastly different and less complex than before. Some plants, insects, and small animals managed to adapt, but many of the large species with specialized roles could not. The loss of biodiversity meant that ecosystems were left with fewer players, which delayed recovery as Earth tried to rebuild its communities of life. In modern conservation, biodiversity is seen as a safeguard against collapse, with diverse species providing a kind of insurance for ecosystems. When a wide variety of plants, animals, and microorganisms inhabit an area, they create resilience by spreading roles across many species. If one species faces a challenge, others can help fill its place, allowing the ecosystem to remain functional even under stress. Habitat loss, deforestation, pollution, and invasive species are all threats to biodiversity, reducing the range of species in many ecosystems and increasing their vulnerability to changes. Just as the loss of plants and animals weakened ecosystems for the dinosaurs, the ongoing reduction in biodiversity today makes it more challenging for modern ecosystems to adapt to climate change and other disruptions. The asteroid impact is thought to have caused sudden temperature drops, firestorms, and the release of soot and particles that blocked sunlight for months or even years. This drastic shift in the climate meant that many dinosaurs, plants, and other animals could no longer survive in conditions that were suddenly colder and darker than they had adapted to. These temperature and light changes, while rapid, bear similarities to the more gradual yet relentless climate shifts seen today. Although the current changes in climate are not caused by a single impact, the effects, rising temperatures, shifting weather patterns, and changing ecosystems, pose similar challenges for life on Earth. One example of this is the threat faced by species in polar and high-altitude regions, which are particularly sensitive to warming temperatures. As ice melts and temperatures rise, animals like polar bears and snow leopards face habitat loss, while plants adapted to colder climates are pushed further up mountainsides in search of suitable conditions. For the dinosaurs, the rapid cooling and darkness caused by the asteroid impact removed habitats that could support them, forcing survivors to move, adapt, or perish. Today, animals and plants facing similar pressures must adapt quickly, but with humans continuing to impact the environment, this task becomes more difficult. In the modern context, scientists warn of an ongoing sixth mass extinction, driven largely by human activities. Unlike the asteroid impact, this extinction is happening gradually but could lead to similar outcomes if biodiversity loss continues unchecked. The ecosystems that remain after such events are often simplified, with fewer species and less genetic diversity, making them more vulnerable to future changes. By studying the dinosaurs and their extinction, researchers can better understand how to prevent or mitigate similar outcomes today by protecting species and habitats, conserving biodiversity, and slowing the pace of climate change. The plants, animals, and even microorganisms that managed to endure did so by finding niches where they could survive the extreme changes in temperature, light, and food availability. They tended to be smaller, more adaptable, and less specialized than the dinosaurs, able to feed on a variety of sources and reproduce rapidly. This adaptability is a key insight for conservationists today, as it shows that species with a broader range of tolerances are often better suited to survive environmental changes. Adaptability to different climates, varied diets, and flexible behaviors are traits that can increase survival chances. When species have these traits, they are better equipped to endure habitat changes, food scarcity, or temperature fluctuations. By understanding which traits helped some organisms survive the dinosaurs' extinction, scientists and conservationists can better prioritize which species to protect and how to manage ecosystems in a changing world. The science of de-extinction. Could we resurrect dinosaurs? In a world where technology is advancing faster than ever before, the notion of de-extinction, using genetics to revive extinct species, has shifted from fantasy to a field that scientists actively research. While most de-extinction efforts focus on animals like the woolly mammoth or the passenger pigeon, it is natural to wonder if one day the same tools could be used to resurrect dinosaurs. At the heart of de-extinction is the science of genetics. To bring an extinct species back to life, scientists need to understand its DNA, the genetic blueprint that guides every aspect of its biology. For recently extinct animals like the woolly mammoth, researchers have been able to find relatively well-preserved DNA from remains that have been frozen or mummified. This DNA can then be compared with the DNA of a closely related modern species, like the Asian elephant for the mammoth, which serves as a genetic foundation to rebuild the extinct animal's traits. But dinosaurs disappeared over 65 million years ago, and unlike mammoths, no complete dinosaur DNA has ever been found. Over time, DNA breaks down, and for organisms that lived millions of years ago, what remains today are only faint traces, often too degraded to offer a full genetic sequence. The oldest known fragments of DNA discovered so far are environmental DNA samples dated to around 2 million years ago, discovered by an international team of researchers in 2022. However, some believe that the DNA problem could be tackled using indirect methods. One approach is to examine birds, the closest living relatives of dinosaurs. Birds inherited a lineage directly linked to certain dinosaur species, carrying within them remnants of ancient genes. By studying avian DNA, scientists hope to identify genes that control dinosaur-like features, like scales, teeth, or claws. This concept is often called reverse evolution, the idea of tweaking genes in birds to activate dormant traits that their dinosaur ancestors once had. Already, scientists have managed to create chicken embryos with somewhat dinosaur-like snouts, and experiments have hinted at the possibility of more complex changes, though much work remains. One challenge with reverse evolution is that it's unlikely to recreate a specific dinosaur. Instead, it may result in something closer to a bird, with a mix of dinosaur-like features, not an actual, true-to-history dinosaur. The genome of a bird is a long way from the genome of a Tyrannosaurus rex, and while certain genes may bring out ancient traits, they won't reconstruct the full structure or behavior of a long-extinct animal, raising the question whether a de-extinct dinosaur would even qualify as a dinosaur at all. It may look the part in some ways, but without the actual DNA that shaped its biology and behavior, it would be more like a distant shadow of the real creature. In addition to reverse evolution, there's also the idea of piecing together DNA fragments from ancient fossils. Although no complete dinosaur DNA has survived, small bits of ancient protein or genetic material have occasionally been found within fossilized bones. For example, in some fossils, scientists have detected collagen, a protein found in bones and connective tissues. Studying this collagen has given researchers clues about the relationships between dinosaurs and modern species. However, proteins alone are not enough to revive a species. They provide only a small part of the picture compared to full DNA sequences. While finding and analyzing these fragments can give insights into dinosaurs' biology, it's far from sufficient to recreate a living animal. De-extinction raises plenty of thorny ethical questions as well. If scientists were ever able to recreate a dinosaur, or even a dinosaur-like animal, where would it live? Dinosaurs thrived in ecosystems vastly different from anything on Earth today. The climate, vegetation, and even the atmospheric oxygen levels were all suited to the needs of these ancient creatures. Reintroducing a dinosaur into the wild would be impossible, as there is no suitable habitat where it could truly thrive. Without the vast landscapes and specific ecological roles they once had, a dinosaur in captivity would be a relic rather than a true revival of the species. Dinosaurs, especially the larger and more carnivorous ones, had no natural predators besides other dinosaurs. Their behaviors, driven by instincts and environmental cues, would be challenging to predict in a modern setting. A large dinosaur, for example, might pose a serious risk if it were released into a confined area or escaped from containment. While some people imagine de-extinction as a chance to see dinosaurs roam again, the practical and safety concerns make it a complicated endeavor. If dinosaurs were to be brought back, they might experience health issues or fail to adapt to the present-day climate and food sources, leading to suffering or shortened lifespans. Some argue that instead of focusing on bringing back long-extinct species, efforts should go toward conserving species currently on the brink of extinction. Conservationists highlight that many animals today face habitat loss, climate change, and poaching, pushing them closer to disappearing forever. The time, money, and technology required to attempt de-extinction could instead be used to protect existing biodiversity, preserving species and ecosystems that play active roles in our world. Supporters of de-extinction, on the other hand, argue that the science itself is valuable and that understanding ancient DNA and genetics could help with conservation by applying knowledge gained from ancient species to benefit endangered ones. Some also raise the question of whether it's humanity's place to correct extinction events. While human activity has been responsible for the recent loss of numerous species, the dinosaurs' extinction was a natural event, part of the planet's long evolutionary history. Some people feel that bringing dinosaurs back would disrupt the natural order. By attempting de-extinction, scientists would be taking on a role typically reserved for evolution itself. The process of reviving a dinosaur, if even remotely possible, would involve choices about which traits to focus on, which environments to simulate, and how the animal should behave, making it a carefully controlled, human-engineered version of life. The idea of seeing a living dinosaur certainly appeals to our sense of wonder and curiosity. Yet this curiosity must be balanced with responsibility, as de-extinction technology could bring unintended consequences. Could this technology lead to a trend of creating designer species for entertainment or novelty? And if so, where would the line be drawn? What side of the argument do you align with? Comment down below, and if you enjoyed this video, consider leaving a like and subscribing to the channel. Thanks for watching.